Hi, and thank you for coming to my talk. Today I want to tell you about our or how Rust got into Volvo Cars and that whole journey. It's quite poetic, I think, that given how everything is upside down these days, that we've spent 100 years trying to keep Rust out of our cars, and now we're starting to embrace it. By the way, this is the EX60 that will be revealed in January. A bit of a teaser there. There's this quote from Graydon, the original creator of Rust, which I really like. It says, "Technology from the past comes to save the future from itself," and it kind of highlights what Rust actually is. It's not that there are not that many novel things. It's actually bringing mostly old technology, but the fact that they are basically combining it in a way that is really well crafted and works together as a really coherent whole. And if I were to do like a car industry take on that same quote, it would be, "The nemesis of our past comes to save us from our future." But anyway, so a little bit about me. My name is Julius Gustavsson, and I'm the system architect and team lead for this low power processor team that is the first Rust-based ECU in the industry. And the ECU is the electronic control unit, for those that don't know. That's the basic building block of an electrical system in a car. I've been at Volvo since 2017, and the obligatory disclaimer that all of my opinions are my own should not reflect my employer. And I've been doing this stuff for over 20 years in different industries. And I actually think that Rust is the biggest deal in our industry during my whole career. And I should say I have some perspective. I've been doing mostly C and C++, but a bunch of different languages that I can compare to. We'll see if AI will push this off the pedestal, but not yet at least. So we're going to start by just going through the origin story and how this all started, and then we'll go to some of the results that we can show and reflections around that, and then we'll look to the future and see how everything is looking out. Does that sound good? Yeah, great. So this is what AI considers an enthusiastic programmer, and this could have been me back in 2015. I had been doing embedded C and C++ for 15 years at that time, and was starting to get really frustrated with these obscure memory bugs always popping up at every turn. And now I was at this new job where I was really impressed with their rigor and their engineering methods. And I was like, okay, finally I'm at a place where they actually have this nailed down, and I don't have to worry about these kind of issues anymore. And spoiler alert, it took about a week, and then I was back into that kind of debugging. So I had this really visceral feeling, like Melvin here in the movie, like, is this as good as it gets? Should I just come to terms with that, things aren't gonna get any better? But then just a few weeks or months later, this came out, the Rust 1.0, and that's when I started reading about it, and it looked really promising, and I actually tried to pick it up a couple of times, but it never really stuck. So I put it on the shelf for a while, and then fast forward 2 years, during my summer vacation, I decided to really dive in. So I read the 2 books that were prevalent at the time, and read them cover to cover, and that's when it finally clicked. And when it did, I was totally convinced that this is something. So I was back to this guy, and this is exactly where I started at Volvo, and I was convinced that Rust would be exactly what the car industry needed, because they were actually they were trying to forecast where the trends would be going in terms of automotive software, and as you see there, the traditional functions, the things that we have been dealing with up until now, that is like steering and braking and propulsion and those kind of things, those are actually projected to stay mostly flat. but it's these other areas like communication, infotainment, autonomous drive, those kind of things. That's where all the growth is going to be happening, and we don't have the tools that were used for the traditional things like model-based programming and those kind of things. Those don't really work. So we need to start to look at new tools for that. So I was really sure that Rust would be a key player there. This is the SPA2 platform that we ended up building. I'm not going to go into any huge details there because that's going to require a whole talk on its own. But the black boxes there, those are the traditional ECUs. And what's different with this architecture is that those are connected via CAN or LEAN, usually connected to these integration units, which then convert those messages to Ethernet and send it to the core computer where the centralized decisions are taken. But when I started, things looked more like this. So we hadn't built out anything. So the core computer was actually just a glorified Raspberry Pi. And we had a couple of CAN interfaces that we could just connect some ECUs at random and try to get things to work. And here we wanted to, for example, send commands from the UI in the infotainment system to do some action in the car, and for example, to control the fans or the AC or something. So we needed a custom vehicle HAL implementation in Android. And I happen to have a lot of Android experience, so I decided to, why not build that in Rust as a first try? This turned out to be quite an undertaking because first I had to get Rust to build on the Android system, because even though Rust is well supported today, it didn't exist at the time. I was doing gRPC communication with the core computer, and I was using futures to do like async programming in the old days of async Rust. And it took me probably a week and a half to get all the scaffolding up and running and working and get this just to compile. But that's the first time I actually experienced this. When it compiles, it works, because when I took the code to the car, plugged it in, I was able to start the fans on the first try. And never happened to me before, never. It was crazy. But yeah, so looking at how they started, so now we're almost 2 years again ahead. I gave a talk at Volvo Cars about Rust and how it could be a key differentiator for our company, and I was actually able to convince a couple of managers that we should actually try to find an opportunity to try this out. And I was also really fortunate to meet another developer who was on the same page, and we joined forces and started looking. And at the same year, they announced the 2018 edition of Rust, which turned out to be really consequential for us, as we'll see later. Then in 2019, we got the green light to try it out. We scouted, and we come to that, for a target where we could use it, and we identified this low-power processor. We went to OxidizeConf, which is today the largest conference for applied Rust, mostly embedded things. And that's where we met key people that would then help us out. For example, the people behind Arctic, which is the operating system, within quotes, that we run on, and other experts that we actually ended up hiring. And just to test the feasibility of all this, we did a master thesis where we tested the viability of no standard Rust, and that was very encouraging results. So we formed the team and started from there. The same year, this report came out from Microsoft. You've probably seen this 100 times. It talks about vulnerabilities discovered in Microsoft products from 2006 to 2018. And the dark blue part is memory-related vulnerabilities, memory safety-related vulnerabilities. And as you can see, there's a line there at 70%. And this 70% line is quite significant because it turns out to be almost a universal constant in projects, C and C++ projects that have reached a certain scale. But 70% doesn't say much, because if the overall vulnerabilities are constantly going down, then 70% of that is also an even smaller number. So maybe it's not a problem. But when you look at the actual data, the amount of vulnerabilities being discovered is actually going up significantly. So this is a huge issue. And the remedy that they proposed in this article was actually to shift to memory-safe languages. So we were quite encouraged that we were on the right path there. Now, when trying to find a place where we could run Rust, things didn't look that great. Everything was basically red. We didn't have Rust support in any of the ECUs, any of the systems. Android didn't have Rust support at the time. And basically, that only leaves the core computer left. And if we look inside the core computer, it's basically a box composed of 5 different CPUs that are responsible for different domains. So we have the high performance node, which is the NVIDIA Orin, the big beefy compute with a lot of GPU, NPUs, a lot of firepower. And then we have 2 high integrity units. Those are the Infineon Tri-Core automotive, high safety for like where you do braking and steering and those kind of things. And then we have a security gateway for basically acting as an edge router between the unsecure world and the secure world. And that one is actually running a Linux distribution. But looking at the available support there, didn't look much better. We had theoretical support. Given it was Linux, we could theoretically run it there, but the Linux distribution that we were using didn't have Rust support. So that left the low power processor. And that happened to have, it was a Cortex M4 controller, microcontroller, which due to the 2018 edition was now possible to do in stable Rust. And Cortex M4 happened to be the most well-supported architecture at that time. So yeah, if we look then at the LP itself and what it's doing, so its main function is to power on this core computer, because the core computer itself draws a lot of power when it's running. So we want to keep it off as much as possible. And we want to turn it on when it's supposed to turn on and not when it's not supposed to. So robustness is key here. It's supposed to facilitate keep some communications channel open while the core computer is shut down. And one thing that makes it suitable for Rust at the time, because there wasn't any safety certification for Rust, the fact that this is constructed in a way that we can turn power on, but we can't cut power. And because if we could cut power, then all of a sudden it would be really safety critical. But given that that is not the case, we didn't have a safety rating, and also the overall functionality or scope of the functionality was fairly limited. So it was a good target for a small team, and also the fact that everyone else was busy getting everything else up and running, so no one was paying attention to this one, so we were able to kind of sneak under the covers. It's connected to these other CPUs via UART, so it communicates via UART, and then it controls a bunch of electronics on the board through GPIOs and I2C and other things. And then a slight tangent on building the actual team. So we were 4 initially, scaled up to 6, and then 8, and then 10 at the peak. But we were all experienced engineers, but none of us had any Rust experience. But we have consistently found that having Rust experience is not a prerequisite to become a Rust engineer. We have shown that you almost any engineer that has these qualities like humility, curiosity, willingness to learn can pick it up in a couple of months, given the right guidance. Because if you don't have the right guidance, it can be a bit like this when you're dealing with a compiler. So yeah, getting the correct experts on board from start is highly recommended. But yeah, back to the LP. So this is what we ended up building. So we have this chip from Microchip called ATSAM E51. It's then running 100% Rust-based firmware based on Arctic, and then we have the C++ component running on the high performance that basically acts as a facade so that we can communicate over IP, convert that through UART, and do other communication with the rest of the system. Yeah, and then we or maybe you see that already. Trying to test our system on this board is really hard because there are so few direct connections to the chip. Everything is going through UARTs and GPIOs on the board, and so we would essentially have to have like a distributed test system where you have like test code spread out on the different CPUs and trying to probe it from different angles, and that just wouldn't scale. So we tried to come up with some hardware that would make this easier. And this was our first attempt. This is the processor in the loop 1.0, we call it. So here we use an off-the-shelf dev board called X Pro for this chip, and a Raspberry Pi to drive the actual I/O and everything. But as you probably see already, this doesn't scale. I mean, after 5 units, this became a nightmare. And also, since the dev board isn't running in the same pin configuration as we have on the board, we had to have a separate binary for this hardware compared to the actual one, which made it a bit of a hassle. And I tried debugging when one of the wires comes loose in like 5 or 10 of those. Doesn't scale. So we talked to our Rust experts who happen to be hardware experts as well, and they convinced us that we would be able to build something much more tailored to our use for basically the same cost. So then we came up with this, which is the Peel 2.0, where basically they're up in the right corner. We have basically the circuit from the core computer, just copy paste it there in the corner, and then we have all this test circuitry around it so that we can probe and prod, and we can debug, we can run CAN, we can do basically whatever we want. We even have these relays to simulate crystal failures and things like that. And the nice thing about this is it costs around €200 to make. Every developer can have one on their desk, and then we can have 100 of those in CI. And they also stack very nicely, so we can create these big rigs with a lot of test hardware, and where we can bombard, or basically all our commits are run against these targets. And the nice thing here is that the actual binary that we test here, we can just ship unmodified to production, and it just works. We never see, or hardly ever see, issues in the actual hardware that we don't see here, which is really nice. And now that all the puzzle pieces were in place, we could start to deliver. And after about a year, we released the first UDS server. UDS is the Universal Diagnostic Services. It's a standard that all cars use. It's the way how you do software download, diagnostics, things like that. So when we had that in place, we could start pushing out our software to the organization, and they could download it to the cars and test rigs and other things. Then in 2023, we were at 1.0. That's where all the cybersecurity and protocols and other mandatory mechanisms were in place so that we were allowed to put it in an actual car for a customer, so that we were allowed to production sign it. And this was a huge milestone because up until this point there was a lot of unknowns if we would actually make it or not. But yeah, everything went super smooth. And meanwhile, these kind of statements started coming out from government bodies, from consumers, from all kinds of organizations about basically requesting that we need to start to move from memory unsafe languages because this 70% trend is just not coming down. Even today, it's still basically intact. And I foresee that this is going to get or become more and more because, I mean, what if CrowdStrike, for example, happened to be an actual hack? I mean, they would probably be breathing down our necks pretty heavily by then. So the question is, do we want to be proactive here, or do we want to get taken by surprise? And also the same year, this report came out from Android and the security team at Android, where they basically show that reversing this 70% trend is actually possible. On the left there, you see how the blue bars are increasing every year, while the red, which is memory unsafe code, is basically tapering off. And direct correlation with the increase of memory safe code, the number of vulnerabilities discovered per year just started declining. And there on the right, you can see that the correlation between new memory safe code and vulnerabilities is also directly related. So this was a good finding as well, and reinforced our position as well. So yeah, and then in 2024, we had our first production release for the Polestar 3. So this was then 3.5 years from literal scratch, where we had not a single line of code, and 3.5 years from zero to production is a fairly good metric in automotive terms. And here we actually see a picture of the core computer, and you can even find the LP there up in the corner. Yeah, so that brings us to the present. So where are we now? We are basically finalizing the last features, and we're wrapping up and basically going into maintenance mode. But that doesn't mean we're going away. We are in the SPA2 and SPA3 platforms, so basically all car models that we will launch going forward will have this Rust code running. And at the same time, we're actively scouting for new opportunities within the organization. We're also getting a lot of interest from different places in the organization after having seen our results. Speaking of results, so yeah, we have the first Rust ECU in production as far as we know, and now I've been speaking to a lot of people in the automotive industry, and this seems to be correct. We've done this with between 6 and 10 developers during the lifetime of the project. It's about 170,000 lines of code. Of that, 90-ish thousand lines of Rust, plus 70 odd third-party crates. And yeah, we designed and built our hardware. We maintain our CI. And we've had to develop a lot of things from scratch because the automotive ecosystem didn't exist basically. So we had to invent bootloaders and protocols and CAN communication stacks, diagnostic stacks, and a bunch of other things. In particular, requirement tracking and tracing, which is a huge deal in automotive. You have to be able to basically every requirement needs to be traced to code and a test that actually verifies that code is doing what it's doing, and there wasn't any tooling to do this properly. And then on top of all that, we actually needed to do the actual LP functionality as well. but then coming to then productivity and quality and things like that. So there was this talk from Google at Rust Nation last year from Lars Bergström, where they showed their findings after they had multiple hundred developers switching from C++ to Rust, and they saw 2x productivity gain compared to C++. And they also saw this higher confidence in correctness. So people feel more confident that the code that they are delivering is actually doing what it's supposed to do, which in turn makes code review easier, and individual contributors basically have higher confidence in what they're doing, which is plus all around. And when we try to compare this to those statistics, we only have one project, so we are just a sample size of one, meaning that everything is really anecdotal still. And also, when comparing productivity, it's hard because we are the only ECU doing exactly this. But we have a lot of other projects who are doing similar things, similar on the complexity scale, and also basically every ECU. 70% of the requirements are the same for every ECU because you have to do certain things to be able to function in a car. So we took the teams that were doing similar things in different environments, but were building it from scratch like we were, and compared basically how many people total project cost, and there we saw a 2 to 4x improvement compared to other teams. And then the other ones, there we can basically just say check, because we don't, they're quite subjective, but in our team we have a combined experience of over 100 years, so we've been doing this for a long time, and everyone agrees that these findings are correct. But just to give some sort of metric to show you that it's actually not just some mumbo jumbo, here is the actual chart of our inflow of externally found bugs, that is, or issues, meaning issues that we didn't discover ourselves, but were discovered somewhere later in the chain. And it's probably hard to read, but the grand total is 23 to date. And when we got to production, it was 18. And to put that in perspective, that is around a half a bug per developer per year, or 0.25 bugs per 1,000 lines of code. And this same metric is around 15 to 50 in a standard software project. So this is like 2 orders of magnitude better than that. And then people ask us, like, why is it? Is it Rust? Is it the fact that you have this awesome hardware that you can test on, or is it just the fact that you have this awesome team? And my answer is yes to all three. But I really think that Rust is the X factor here. And because we see that both in the ecosystem itself, with these super high quality crates that you can find in the ecosystem, but also just that it kind of feeds this virtuous cycle of improvement and empowerment that just everyone feels a drive to improve and make things better, which I think is great. And then you might think to yourself, oh wow, he's overselling it, and maybe I am, but Rust is not perfect, that's for sure. The learning curve, for example, is real. You need to take care of that, but it's not nearly as bad as many claim. And like I said, 1 to 2 months is usually what it takes to get people up to speed, given that they get the right guidance. I find the most difficult part is to basically unlearn a lot of bad practices that you've picked up during your career. That you can maybe reason that it's fine in this particular case, but it's never fine in the grand scheme of things. And these things you need to like reevaluate and re-educate yourself. Yeah, and also there can be some cognitive load, because it can be frustrating sometimes that it doesn't compile, and you're often in these type Tetris kind of games where like trying to make all the types fit and all that, and it can get frustrating at times, that's for sure. But and also build times could be better, binaries could be smaller or aren't as small as they could be, and also there are still a lot of things that are still being fleshed out in the language. But the positives just vastly outweigh the negatives. I've ever since we started, I've always been like looking for this like catch, like is there something that just makes everything come crashing down, all of these assumptions? And so far, I've only seen the contrary. That we're just seeing more and more positive signs that this is the way to go. So yeah, the verdict. Basically, huge success. But I wish I could say that now we're just rolling out Rust everywhere and it's just in the bag. But if you remember, for those of you who grew up in the 80s and 90s, remember when we used to have video cassettes, Be Kind, Rewind, and all that. Everyone had VHS, but at the time, Betamax was the contender, and it was actually the technically superior contender, but it just got wiped out by non-technical issues. So the same here, that even though we're seeing all these results, it's not like it's just automatically picking up. So we need to push this forward and make sure that this is going to fly. And one of the things we need to be more bold is that especially the car industry is really keen on just going to a supplier. They present us with a working solution, and we just take that, put it into production, and that doesn't always exist here. So sometimes we need to be bold and not be afraid to build that out ourselves, and hopefully contribute that back to the community as well. And that brings us to future outlook. So now, when we look at how Rust support today compared to before, where everything was basically red, now everything is mostly green. We have a few exotic automotive architectures that still don't have Rust support, but overall it's looking much better. And also, if we look at the different software stacks that we're running in the car, we have our low power processor there, and now we have Rust support in Android, but basically all the other stacks are now ready to use it. So we have QNX support, we have AutoSAR support, and there's almost no environment left where you can't use it. But now let's talk about safety critical, because that is the topic that I haven't mentioned yet. And automotive is of course a safety critical industry. And safety critical certification is something that takes time, and it's quite ironic that you have a language that is pretty much superior in every way for these kind of applications, but the certification is not there yet. But it's coming along, and just last year we started the Safety Critical Consortium as part of the Rust project, and who are working on coding guidelines and try to fill the gaps in the tooling and things like that are needed. We have compilers, certified compilers from Ferrocene, from High Tech, and I think from some other vendors as well. So the compiler part of it is coming along. We have the specification from Ferrocene that was donated to the Rust project that is becoming the official one, to be announced soon, as far as I know. And then we have, on the runtime library side, that was just announced last week that Ferrocene have certified parts of the core library to SEAL 2, which is the industrial counterpart to ISO 26262, corresponding to ASIL B in that part. So that is coming along, and then there are some other tooling that are still lacking, but are being worked on. But so my prediction is that 2026 is going to be the year of safety critical rust in cars, and we actually have a lot of projects ongoing certification right now. And I think that Rust has a unique potential in the safety critical space because, and then I want to highlight these two talks from RustConf last year because they are really amazing. Here they demonstrate to an even larger degree than what Helge Penny was talking about this morning, about how you can leverage the type system to actually exhibit or enforce behaviors that you want to see in the system and make unwanted behaviors basically not possible to construct. And in the first one, their Safety in an Unsafe World, they show how they wrote the network stack in the Fuchsia operating system, where they have, I think it was 70 different locks that need to be coordinated in different places, and that is a deadlock nightmare. But they were able to encode the locking behavior and relation between the different locks in the type system. So you basically get deadlock-free behavior at compile time, which is pretty cool. And the other one is about transmute. Transmute is the void star of Rust, something that you should never use, except in very specific circumstances. But here they are basically doing that in a safe way by using the type system to actually enforce that you have ensured that alignment is correct and the lifetimes are correct and the bits actually contain the right data and so forth. This kind of exhibits what Rust is striving to, that is correct by construction, which is another way of saying what Helge was saying this morning, that Rust makes programs, or hard to construct programs that are wrong. Here we say correct by construction. So the fact that they actually compile means that they actually work as intended. And I think that we can even apply this in the safety critical space by going to compliant by construction. How about if we could basically ensure that all the safety invariants are also upheld just by virtue of it compiling? Because that means that all the runtime activities that you have to do afterwards to verify things that things are correct just aren't needed. And of course, this is not going to be possible for everything, but I mean, the more we can do, the better. And of course, money is always the deciding factor. And today we are spending about 90% of our development effort on verification. And the industry itself spends around 2% of its revenue on warranty costs per year. And that's around $50 billion per year that the current industry spends. So imagine if we could bring this down to, say, 20%. That's like $10 billion right there. And anecdotally, from what I've heard in projects that are undergoing certification, that they are seeing around 50% reduction in effort to certify their components. That's of course still going to be, it needs to be verified, and we'll see the actual numbers when they are done. But it's looking really. So imagine having 50% or 2x productivity increase, and then half of the effort to certify it. I mean, then it's just a no-brainer. So yeah, I mean, we're literally talking about billions in savings. One note about safety versus security, because we have this distinction between safety that we call functional safety, that is that the product is safe to use and it doesn't cause harm, or we try to avoid harm at all costs, and then cybersecurity, where we want it to be safe from hacking. And of course, security is like mandatory in order to ensure safety. So they are tightly interlinked. And over the years, the various different industries have come up with basically a process to ensure that the products actually adhere to this to ensure that they actually are doing what they're supposed to. And it's interesting when you like look at the core bits of those things. It's of course much more complex than this. This is just a really high level 20,000 foot view of it. But they basically go hand in hand. So on the safety side, you perform a hazard analysis, a HARA. On the security side, you do a threat analysis, a TARA. And then you define your safety goals and your safety case. Same for the security part. And then you have these strict guidelines on how you develop your code to ensure that it's, within the bounds of well-defined behavior, and then you have extensive testing, verification, and all that. So all of these are like mirroring each other until you come to the final point, because on the safety side, when you certify it, it's such a costly effort that you never want to touch it again once you certify it. So like you avoid doing any sort of modifications afterwards. While on the security side, you really want to keep it up to date all the time to get any vulnerabilities and things that are discovered fixed. And these are like fundamentally at odds. And so I think that Rust can actually be the solution here, because on the one hand, you have the type system and you have all these things that the Rust language gives you that allows you to both refactor without fear, like we were talking about this morning, and you have much more control over what changes you did and that they're actually not affecting anything else, things like that. So meaning that if you need to do a change, recertifying that delta should be much less effort than used to be before. But on the other hand, the correctness is also much higher up front. So the fact that we aren't seeing this long tail of bugs, over the lifetime of the project. So we're not gonna be needing to do all of these updates in the same frequency. So yeah, the future for Rust in cars is bright. There's no other time in my career that I can remember where we can do this simple shift and we get better quality, better security, higher quality, lower maintenance cost, lower warranty cost, lower license cost, productivity, happier developers, and attract talent all at the same time. And with that, I want to thank you, and we can go to questions. Yeah, I can start. I can repeat the.
Okay, so early on in the talk, you mentioned that you're using roughly 70 third-party crates
Yes.
in the project.
Yes.
So I'm curious, how does the company handle secure supply chain issues, doing crate auditing and reviewing, and all this process around compliance with external code?
Yeah. So we. That is a really good question. So the question was, how do we deal with third-party crates? How we audit them? How we ensure that we have a safe supply chain of third-party crates? So first of all, we have everything is mirrored in our own crate repository in-house. So and we only pick in versions that we have vetted, and then we. So most of these 70 are actually very, very simple crates that is really easy to audit and see that they're actually doing what they're supposed to do. But yeah, we have we go through them license-wise, code-wise, and and then we have cargo audit running continuously to detect any issues, vulnerabilities or otherwise that show up. Yeah, basically that's what we're doing today. Hope that answered. Yeah, and we also have then SBOM generation in place so that we can always track that to see what went into every car. And yeah, exactly. Yeah. Any other question? Oh, start back there.
Does Rust have good support for communication protocols like Ethercat, CAN?
Ethercat, I'm not. So the question was if Rust has good support for communication protocols. That is improving all the time. So now we have a lot of CAN support. We actually contributed MCAN, which is a CAN peripheral from Bosch that is found in many of the MCUs out there. So that is the low-level drivers for that. And yeah, so I would say on the CAN side, it's definitely improving. We have small TCP for Ethernet, but EtherCAT, I'm not sure. But the nice thing is that you can build it yourself and contribute it as well. So and we shouldn't be afraid of that either. So yeah.
You showed a nice slide with all the chips and components of the car that are now Rust ready.
Yeah.
But there's also political side to this. Like, how is it going to convince management and convince the other developers inside Volvo that this is where we want to move, we want to get Rust on all of these things? Is that still an uphill battle, or is the success of your low power component really helping you to sell this inside the company?
Yeah. So the question was if how well or how easy it is to convince the rest of the organization to switch to Rust, given that the car industry is a super conservative industry. So yes, that has not been easy. I can just say that up front, and it's definitely a lot of days where you feel like Don Quixote, fighting with windmills. But it's definitely turning around. I mean, and just in the last year, I mean, you see at Rust conferences now, you have a bunch of automotive players, industry, defense, aeronautics. I mean, everyone is getting in on this. So and just seeing the numbers, I mean, it's really hard to ignore. I mean, for example, AI is projected to save around 20 to 30% overall, and the world is going bonkers. And I mean, here we're talking about at least that. So I mean, yeah.
What part of the core library do you use? The allocator part, or just the base core?
Yeah, the question was if we use the allocator part. That is actually a separate library. So the core library is without allocations. We are only using core. So no dynamic allocations. But what we have creates like heapless, for example, that gives you the feel of a heap, but everything is on the stack. And then we have a hardware-based Stack Overflow protector that in case we would run out of stack. Yeah. Did I see a hand here? Victor?
Are there any components that you're currently working on, maybe it wasn't the LD one, where you had to do some kind of gradual Rust adoption in an existing C or C++ component, as in, did you need to interact with existing either internal libraries or components or some sort of internal situation?
So the short answer is no. When we started out, and I forgot to mention that earlier, we actually had prototype C code that we got from the device manufacturer that we could use to actually start the core computer, so that everyone else could get up and running, and that had some basic functionality that we wanted to use as a base, and then we were going to build Rust on top of that. But actually, though it worked, we were always seeing issues actually on the C side. So we decided to rip that out and just write everything in Rust. So now we actually don't have that problem. I did a fair amount of that in this Android proof of concept that I talked about. There I was doing a lot of interacting between C++ and Rust and back and forth. The C++ to Rust story is still improving, let's say, and there's a lot of effort ongoing in the community to improve that. You can always go through the C API, and that one is pretty much zero overhead. But as soon as you cross that boundary, you don't have any. The compiler can't. I mean, all bets are off. So you need to be really vigorous in those. Yeah, in those interactions. So it might make more sense to use maybe shared memory or some IPC or some other way of basically isolating the two parts. But it depends on the problem at hand. And
so you're mostly targeting greenfield Rust rewrites or wholesale components in Rust.
Yeah, so we're mostly doing. So this project was a complete greenfield. For new projects, that will never be the case because now we have a bunch of legacy code, and I'm not advocating for rewriting everything in Rust. That is just a dumb statement, because most of legacy code is there for a reason because it works, and most of the time it's not worth it to rewrite it. I mean, there might be parts where it makes sense. For example, if you're parsing, external user data or untrusted data of some sort, those kind of things, it might make sense. But in general, that is not a strategy I would recommend, but rather to focus new development on the Rust side. But that still means that you need to interact with the old code, and so that is something I look forward to tackling in future projects. Okay, any more? All right, doesn't look like it. And thank you very much.